Hello everyone, myself B. Vijaya, lecturer in chemistry, working in Indira Priyadarshini Government Degree College for Women, Nampalli. And today we are going to discuss the coordination compounds. The coordination compounds In the coordination compounds, we are discussing the Valence Bond Theory, which was first explained by Linus Pauling. And he was an American chemist, biochemist, peace activist, author, and educator. He was one of the most influential chemists in history and ranks among the most important scientists of the 20th century. Pauling was among the first scientists to work in the fields of quantum chemistry and molecular biology. Pauling is one of the only four individuals to have won more than one Nobel Prize. He is one of the only two people awarded Nobel Prizes in different fields, that is, chemistry and peace. The other being is Madame Marie Curie. She won the prizes, Nobel Prizes in chemistry and physics, but she won in the share. Linus Pauling, he was the only person awarded two unshared Nobel Prizes, and he was the father of modern chemistry. And what is Valence Bond Theory? And before going to discuss about the Valence Bond Theory in the coordination complexes, so first let us know what is the coordination complexes. What are the coordination complexes are also called as the coordination compounds. So the coordination compounds are uh, the coordination compounds are consist of one central metal one central metal ion, and which is surrounded by a the negatively charged or the lone pair of electrons they must carry. So the ligands are called as the ligands. So they are surrounded by certain number of ligands here. Metal atom, central metal atom or ion in its ionic form or atomic form, which is surrounded by the negatively charged species, are the molecules which carry the molecules or atoms or group of the atoms which carry the lone pair of electrons. So these are called as the ligands, and this is surrounded by the ligands with the one special type of the bonding is called as the coordinate covalent bond. Coordinate covalent bond. And because of this coordinate covalent bonding taking place between the central metal atom or ion and the ligands, these particular molecules are considered as the coordination compounds. And there is a what is special type of the bonding actually. So what is coordinate covalent bond? Coordinate covalent bond is nothing but here the central metal ion metals are usually a electropositive ones, right? Electropositivity means what? They are having a tendency to lose an electrons, so that by losing an electron these metals are having a vacant d orbitals, right? Vacant d orbitals. So this, because of presence of this vacant d orbitals, their sizes will be reduces, so they are having a smaller sizes, right? And because they are losing the electrons, since they are losing the electrons, so the proton number will be exhibited, because the any neutral gaseous atom, the proton number will be equal to the electron number. So the how many number of protons will be there means positive charges will be there, the same number of the negative charged species, that is called as electrons, are also present, then only it is considered as a neutral gaseous atom. In this case, in the metal, this metal is losing an electrons to form a vacant d orbitals, right? So because of this electropositive character, so that is the reason this metals exhibits the variable oxidation states. Variable oxidation states. Variable oxidation states they exhibit. So these are the three very important conditions for the metal to form a coordinate covalent bonding. So because of presence of this vacant d orbitals, they are acts as a electron acceptor. So they will, because this metal is having an empty d orbital by losing an electrons from their orbitals, right? So d orbitals are empty to this d orbital, and whatever the ligands are there which are surrounded by the central metal ion, and these ligands are carrying either lone pair of electrons or negative charges. Lone pair of electrons or negatively charged species are surrounded by the central metal cation, and these extra electrons which are ligands are having, so these ligands will share their electron pair to the empty orbitals of the central metal atom or ion. So this kind of bonding which results the bonding is called, special type of the bonding is called as a coordinate covalent bonding. So what is the coordinate covalent bonding? The bonding takes place between the central metal cation, empty orbitals of the central metal cation, and the electron pair donated by the ligands is called as a coordinate covalent bonding. I'm writing this coordinate covalent bonding. This is the special type of the bonding. So because of this bonding, coordinate covalent bonding, because of the this special kind of the bonding, because we know that what is covalent bonding, there is a sharing of the electrons will be takes place, means the mutual sharing of the electrons takes place between the successive atoms. Here also sharing is taking place, but how the sharing will be taking place? The ligands are having a extra pair of electrons, metal here is having a empty d orbitals, so that this ligand is donating this electron to the empty orbitals of the metal, and metal is accommodating, giving the accommodation for the uh, electrons. So this metal is accepting the electrons from the ligand. That is the reason this metal ion is called as the electron acceptor. And since, as per the Lewis acid base theory, any compound or any atom which accepts the pair of electrons from the other element or other atom, that is considered as Lewis acid. So as per Lewis acid theory, here metal is accepting the pair of electrons from the ligand, so that this metal ions are called as the Lewis acids in this coordination compounds, and these are electron acceptors. And since ligands are donating the pair of electrons, so as per Lewis acid base theory, any atom or group of atoms which donates a pair of electrons to the other atom, other species, so those are considered as a Lewis bases. So this is acting as a electron donor. This electron donor, because of this electron donation capacity, these ligands are called as a Lewis bases in the coordination chemistry. So, in Valence bond theory, this coordinate covalent bond takes place between the central metal ion and the ligand. So, to the empty d orbitals of the metal atom or ion, the ligands will donate their pair of the electrons, so that the coordinate covalent bond will be results. The next one is the next postulate in the valency bond theory is, to accommodate the electrons which are donated by the ligands, metal ion should have an empty d orbitals. Already I told you this point, and the empty orbitals of the metal ion hybridize to form a new set of equivalent hybridized orbitals with definite directional properties. So this point I will explain along with the example so that you can understand betterly. So here the empty orbitals of the metal ions will be hybridized to form a new equivalent hybridized orbital. That means the the atomic orbitals of the d atomic orbitals of the metal ion will be undergo the hybridization process as per the number of ligands approaches. So to accommodate the um, electrons donated by the ligand. So it depends upon the as the number of ligands, as per the number of ligands, and metal orbitals and ligand orbitals overlap to form strong sigma covalent bonds. That means the coordinate covalent bonds are here, the coordinate covalent bonds they will form. These bonds are really very stronger than even covalent bonds also, because this bond is forming between the metal orbitals and the pair of electrons donated by the ligands here. So it is a very strong bonds. These bonds are called as a coordinate covalent bonds. And in sometimes the back bonding will be also takes place here. So all these will be explained by the this valency orbital theory. And this valency orbital theory is also giving the information of there is a relationship between the coordination number and shape of the molecule uh, also. So as per this theory, if the coordination number is 2, that means the number of mono uh, means ligands, means only single ligands will be there, monodentate ligands will be there. So the this will be coordination number will be equal to monodentate ligands, right? So here the 2 is there, 2 if the coordination number 2, that means if the central metal cation is surrounded by the 2 ligands only, so it will be a linear shape, linear molecule, right? So this is giving the information about the relationship between the coordination number as well as the shape of the molecule also. And the example for this linear molecules are copper chloride, silver ammonium ion, and aurum chloride, etc. And if the coordination number 4, there are the two types of the shapes, means two types of the shapes will be possible. One is the square planar shape and another one is the tetrahedral shape. One will be the square planar shape and another one is the tetrahedral shape. So square planar means all the atoms, including central metal cation and the ligands, are on the same plane. So that is for the examples. For this shape, the examples are nickel tetracyanide, palladium tetrachloride, platinum tetraammonium platinum, uh, tetra amino copper. Okay, so these are the molecules. And for the tetrahedral, the copper tetracyanide and tetraammonium zinc plus 2 and tetrachlorocadmium ion, tetrachloromanganese ion. All these are the example for the tetrahedral molecules. And for octahedral molecules, the examples are if the coordination number is 6, then it will give the octahedral shape. And for the octahedral shape of the molecule, these are the examples. So hexa aqua titanium plus 3 ion, hexacyanovenedium 4 minus, and uh, dichloro tetraamine dichlorochromium ion, and hexaacomanganese ion, hexachloro iron 3 plus, and diethylamine tri tris, right? Tris diethylamine cobalt 3 plus. So all these are the examples of octahedral compounds. So the first square planar complex, square planar shape, let us see now. Let us apply the valency bond theory for the this particular examples. So here nickel tetracyanide I am taking. The first example, I'm taking square planar, right? Square planar complexes I'm taking, and in that nickel tetracyanide, nickel tetracyanide, nickel tetracyanide, so minus 2, right? So let us see the example. Yeah, nickel tetracyanide minus 2. This is the example I am taking, and let us apply valence bond theory for this particular complex in order to explain its structure and geometry. So I want to change the color of this. So in this, first what we have to know, the first point we need to know is the atomic number of central metal cation. Atomic number of central metal cation, and what is the central metal cation here is, that is a nickel, right? Nickel. Nickel is the central metal cation. And what is the atomic number? That is the 28. So what will be the next point? The next point is the electronic configuration. Electronic configuration of nickel. And here we have to know what is the oxidation state, and let us calculate the oxidation state for the nickel here. And here I am doing the calculation for nickel. There should be a square bracket. It should be closed in the square bracket. So 4 2 minus, this is the complex, right? So we don't know what is the oxidation state of the nickel, we need to find out. And each cyanide is carries a -1 oxidation state. So it is a simple algebraic equation. So nickel is carrying the X. Okay, let us take, we don't know, we have to find out the oxidation state of the nickel here. And plus each cyanide is carrying -1 oxidation state. And how many cyanides are there? 4 cyanides are there, and each cyanide is carrying a -1 oxidation state, which is equal to this charge. This is the anionic complex, so that this negative charge is applied to the complete complex here. So this side, right hand side, I am taking -2 here. This charge, whatever the charge is there here, I am taking here. So x, and plus into minus is the minus, right? 4 into 1 is 4. So plus 4 into -1 will be the -4, and -2, and x is equal to -2, and this -4, if it comes this side, it will become a +4. So x is equal to 4 minus 2. What is the number? So it is a +2. This is the oxidation state of the nickel, right? So since here I am writing the electronic configuration, ground state electronic configuration, that is argon, which is having a 18 electronic configuration, and 3d8 4s2. So the electronic configuration I am writing. And in the third point, let us mention this one, this +2. So now what will be the electronic configuration? Electronic configuration of nickel +2 ion now. So because nickel is in the nickel +2 ion, as a nickel +2 ion, it is there in the complex. So nickel +2 ion. So +2 ion, which is formed by losing the 2 electrons from the outermost orbital here. So from this outermost orbital, it is losing electrons. So it is having a 3d8. There are no electrons present in the 4s orbital. So now fourth point is, so now we know the electronic configuration of nickel +2, and this will be the ground state electronic configuration. And let us enter this electron in terms of the, means in the ground state electronic configuration. So d orbital, which is having a which is composed of 5 suborbitals, actually dxy, dyz, dzx, dx square, y square, dz square. So these are the names of each and every orbital. So this is the ground state electronic configuration, and let us fill the 3D 8 electrons in this ground state electronic configuration. So 1, 2, 3, as per Hund's rule, Pauli's exclusion principle, of Bohr principle, etc. I am following this one. So after filling, means after half filling the electrons, means in such a way that all the orbitals are having a 1 electron in each, then I have paired the electrons. So total 8 electrons in the ground state electronic configuration. And let us write the excited state electronic configuration. Why it should be excited? Because this orbitals, whatever the cyanides are there, 4 cyanides are there. 4 cyanides are there, and here the 4s, because it is lost its electron, right? This is the 3d8 and this is 4s0 now, 4s0 now, and 4s0, and fourth orbital is entered, means 4s is there, 4p is there, and 4d is also there, but they are the empty orbitals, right? So the fifth orbital will be the excitation of the electrons will be takes place. So how the excitation will be takes place? Because they are having a electrons, means cyanide, 4 cyanides are there, so they have to means they have to means provide, they have to accommodate the electron pair donated by each cyanide is donating the pair of electrons to the nickel, so that it has to accommodate, it has to provide the accommodation for the electrons donated by the cyanide ligands here, so that they require a 4 empty orbitals now. So in excitation molecule, this electron will be moved into the this orbital, because they are actually they are in the degenerated form only actually. So this electron, one of the electron, because they are both are the unpaired electrons, no, so it is moving into the this inner orbital here. So because of this reason, it is having the excited electronic configuration. I am going to write now. So here 8 electrons, all electrons are paired, and 8 electrons are there, and this 3D 8 electrons are there, and this one d orbital and one s orbital and two p orbitals, so s and p. Okay, so how many orbitals? Just I will change the color so that we can easily. So these 4 orbitals merge together. So merging together and forming a what is the hybridization? 1d orbital. So this is the excited state. Excited state electronic configuration of a nickel plus 2 ion, and in the nickel plus 2 ion the hybridization is taking place. So what is the hybridization taking place? What will be the hybridization? How many orbitals it is utilizing for the to accommodate 4 cyanide 4 pairs of the cyanide ions. So which is providing a 4, means it should be equal to the number of coordination number. So there will be, it requires a 4 empty orbitals. So these are the 4 empty orbitals. What are the 4 empty orbitals? dsp2 hybridization, and for dsp2 hybridization, this will gives a square planar geometry. Square planar geometry or shape. square planar geometry are shaped. So all the atoms, including the nickel also, all the atoms are in the same plane only. So which is the square planar geometry. And what is the structure of this particular molecule is the square planar geometry. What will be the structure? So here nickel is there, and which is having a coordinate covalent bonds with a cyanide ions, cyanide molecular ions, and which should be in the square bracket. So it is a 2 minus. This is the structure of the nickel tetracyanide. Clear? And what is the next example is copper, tetraamine copper plus 2. Okay, tetraamine copper plus 2. Let us, okay, so the second example in the square planar complexes, that is copper, tetraamine copper, amine copper plus 2, 2 plus. Okay, here the central metal cation is copper, and central metal cation is copper. So the first point is the atomic number of copper, and this is a very important example, actually very important to learn about this particular complex. This is also called as a miscellaneous complex also. So why, I will tell you later, you can understand it in later. So atomic number of copper is 29, right? And second point is the electronic configuration of copper, electronic configuration of copper, actually, which is a 3D10 4s1, right? 4s1, this is the electronic configuration of the copper metal. But here copper is in the form of +2 oxidation state. Why? Because ammonia does not carry any charges. So the for ammonia, it is the zero charge is there, zero charge. So whatever the charge is there on the square bracket in the ionization sphere, so this is formed because of the central metal cation here. So this copper is having a +2 oxidation state. An electronic configuration of copper +2 ion. So in this particular complex, copper in the form of the +2 oxidation state, copper is carrying a +2 oxidation state. That means it is losing one of the electron from here and one of the electron from the this 3D10. So after losing these two electrons, the remaining electrons will be 3D9 electrons will be there. And what is the fourth point here? The fourth point is we need to arrange the electrons in the ground state electronic configuration. Ground state electronic configuration. What is the ground state electronic configuration? If 3D orbital is there and 9 electrons will be there, and 4s orbital is also present, but it is empty because it has lost 2 electrons from the outermost orbitals. And then 4p orbital is also there, but it is also a empty one. And let us see here what is the ground state electronic configuration of the this copper. So this is the ground state electronic configuration, that is the 3D9 it is having, and 1 1 1 1 1 electron, Next, we need to pair up the electrons here in this manner. So we have to pair up, right? So 4s orbital is also there, but it is a empty orbital, 4s0, and 4p orbital is also there, but it is also a empty orbital, right? 4p orbital is also empty orbital. And now what will be takes place? Actually, what it will be takes place. So, because this d orbital is containing only one electron, so we will expect that this sp3 hybridization means this empty orbitals will undergo the hybridization process actually. But here, conversely, what is happening here is this electron, whatever the electron present in the 3d9, this will be jumped into the next higher energy level, that is into 4p orbital. So it is expected to be a sp3 hybridization first, but the X-ray analysis, the structural analysis of the physical analysis like spectroscopic methods are giving the structure which is a not it is a tetrahedral structure. So this the structure of this particular molecule is a square planar molecule. So how it will be? Because for the square planar it should be a dsp2 hybridization, right? And this electron, single electron, is jumping into the 4p orbital. Then after that, so the excited state electronic configuration. Now, what will be happen here? Let us see in the excited state electronic configuration. Electronic configuration. So, in the excited state electronic configuration, let us see now. So, 1, 2, 3, 4, 5 s orbital and 4p orbital, and here 3d9 electrons are already there, and here 4s will be the 0 and 4p is there. So this one of the electron is exciting into the 4p orbital, so that this is having a 8 electrons. So 1 2 3 4 5 6 7 8, and one orbital is remained in the 3d, and this s orbital is there, and in 4p one electron is there. Now these orbitals are undergoing the hybridization process, whatever the empty 4 orbitals are there, and these 4 orbitals are undergoing the this hybridization process, and they are merging together and forming a 4 dsp2 hybridized orbital. So what will be the hybridization? By combining, by merging of the one d orbital and one s orbital to p orbital. So uh, uh, in order to provide the 4 empty orbitals to this ammonia molecule ions. So what will be the hybridization? The hybridization is dsp2 hybridization. dsp2 hybridization, and this dsp2 hybridization, what will be the geometry for the dsp2 hybridization? The square planar geometry. Square planar geometry. Square planar geometry. And what will be the structure of this particular molecule? The central metal cation is in the center, and in 4 corners on the same plane the ammonium molecules will be there. Okay, ammonium molecules will be there, and this is kept under the square brackets. So this is a cationic complex which carries a 2 plus ion. So this is about these are the two examples I want to explain under the heading of the square planar complexes. Is that clear? Then the next one is the tetrahedral complexes. So here the tetrahedral complexes. What are the examples for the tetrahedral complexes? The tetrahedral complexes examples are, for example, the tetracarbonyl, nickel tetracarbonyl, alright. So, nickel tetracarbonyl, and let us see now whether it is a tetrahedral complex or not as per Valence bond orbital theory. So, for the nickel complexes, and this is a nickel tetracarbonyl, the first point, what is the first point? The atomic number of central metal cation, that is a nickel. Here that is 28, right? Second point is the electronic configuration of nickel, that is 3d8 4s2. So, argon 3d8 4s2. This is the electronic configuration of nickel. And here I am not writing the electronic configuration of nickel ion. Why? Because in this particular complex, nickel is forming in its pure form only. That means in elementary form only. Means with a zero oxidation state, it is forming the compound with the carbonyl groups. So, this nickel, it does not carry any charge in this particular complex. And what will be the third point now? The third point is the ground state electronic configuration. Ground state electronic configuration. So, what is the ground state electronic configuration of the nickel? Means this nickel present in this particular complex is that is 3d8 4s2, right? 3d8 4s2, and so we need to arrange these electrons in a order of orbitals. So this is the fourth orbital, 4 s2 electrons are there and 3d8 electrons are there. So 1 2 3 4 5 and 6 7 8 8 electrons. Now you see here this is a 3d8 electrons and here 4s2 electrons are there, means these are the unpaired electrons. It is short of 2 electrons. The 3d8, if it will becomes 3d10, then this orbital will become a fully filled electronic configuration. It will get a stability, right? And this orbital is a paired electrons, and because of it is required 2 electrons, right? So that this electron, one of this electron will pair with this electron, and another electron is also pair up this electron, so that the excitation of the orbitals will be takes place. And if 4s is there, means they are having a 4p also, but 4p is the empty orbital, right? So here in the 3d, it will become the d orbital. The 3d orbital will become a 3d10 now in the excited state. So here 1 2 3 4 5 6 7 8 9 10, and this 4s orbital will become no electrons present, and 4p orbital will become, means it is a, as usual it is a empty one only. Now the hybridization of these orbitals, the orbitals are undergo the hybridization process now, hybridization process. And what is the hybridization is taking place now? What is the hybridization taking place? What are the orbitals are merging together? So one s orbital is merging and 3p orbital. So what is the hybridization? sp3 hybridization. And these are the coordination number 4 molecules, right? 4, coordination number 4. So what will be next point? Immediately, if we know the hybridization, it reveals the structure, that is the tetrahedral structure, right? Tetrahedral structure, tetrahedral molecules. So tetrahedral structure it is giving, tetrahedral structure. And the next one is what is the structure, right? Structure. Here we can even give the magnetic behavior also, since there are no unpaired electrons are there, and this compound is a diamagnetic compound, diamagnetic substance actually. So here it is tetrahedral structure, so that the geometry and what is the shape of the molecule, that's the tetrahedral shape. So nickel is in the middle, that means central, and above one bond. Okay, so here this is actually a typical structure. Tetrahedral structure is a typical structure, and there will be a carbonyl group, carbonyl group, carbonyl group, and carbonyl group. 4 carbonyl groups are there on the inside the coordination sphere, and which does not carry any charges here. So this is about the nickel tetracarbonyl. And I want to give you one more example for this tetrahedral complexes. So the second example is zinc tetracyanide inside square brackets minus 2. So this is the another example, and in this example what will be the first point? The atomic number of zinc. Okay, so that is, what is the atomic number of the zinc? That is 30. Means the zinc here is a central metal cation. And what is the electronic configuration? Electronic configuration of zinc. So what is the electronic configuration? 3d10 4s2. This is the electronic configuration. And what is the oxidation state of the zinc here? So since cyanide, each cyanide is carrying -1 oxidation state. So for zinc I am taking the X. Okay, X is the oxidation for the zinc, because we don't know what is the oxidation state of the zinc, and we need to find out the oxidation state of the zinc here. And X plus, and how many cyanides are there? 4 cyanides are there, and each cyanide is carrying a -1 oxidation state, and 4 into -1, which is equal to -2, and X plus 4 into -1 will be the -4 is equal to -2, and X is equal to this -4 will become +2. It will come this side and become a +4, right? So X is equal to +2 oxidation state. In this manner, zinc is carrying a +2 oxidation state in its this particular complex. And what is the third point now? Yes, we need to write the electronic configuration of zinc +2 ion now. So electronic configuration of zinc +2 ion, because this ion is present in the this particular complex, and this point is more important here. For the ground state electronic configuration, we need to consider this part only, this point only. So it is losing these 2 electrons from its outermost orbital and forming a zinc plus 2 ion. So the inner orbital, that is the penultimate shell 3d10, it will be like that only, and 4s will become 0 and 4p is also there, but it is also a 0. So electronic configuration of zinc plus 2 ions are 3d10, 4s 0 and 4p 0. And now we need to write this electronic configuration in the form of the ground state electronic configuration of zinc plus 2. So in terms of orbitals we need to represent. So how can we represent in terms of orbitals? In this way, right? So 3D orbitals, 5 orbitals are there, and it is having a fully filled electronic configuration, that is 1 electron present in each of the orbital. Then we have to pair up the electrons in this way. So total 10 electrons are there, and 4s orbital is the empty orbital. Okay, 4p orbital is also a empty orbitals only. 4p orbitals also empty orbitals. And what will be the fifth point now? The fifth point is the excited state, right? Excited state. And there is no requirement of excited state actually. So why? Because here the completely 3D orbital is completely filled electronic configuration is there, and whatever the requirement of the orbitals for the cyanides, the electrons donated by the cyanides, they are there. 4 orbitals are also available here. So the merging of the atomic orbitals is taking place here. What are the atomic orbitals are merging together? One s orbital and 3p orbitals, right? So by merging of this 1s and 3p orbitals, it will become a what will be the hybridization? 1s and 3p orbital. So sp3 hybridization, and for the sp3 hybridization the structure will be tetrahedral structure, right? Tetrahedral molecule or tetrahedral structure. And for zinc molecule, so here the seventh point is the structure of the zinc molecule, and zinc is at the center, and in upper side there is a one cyanide molecular ion is there, and these bonds are very typical because any two bonds are perpendicular to the other two bonds in the tetrahedral structure. So this is the molecule formed in the as per the Valence Bond theory. So this is about means the coordination number 4 molecules I have explained in this video. Thank you.